we're going to cover the case of repeated eigenvalues. And there are two types of repeated eigenvalues. Let's start with an example. Let's say we're solving this system of differential equations. dx dt equals x minus 3y. dy dt is 3x plus 7y. The procedure is first isolate the coefficients matrix. 1 minus 3, 3, 7. Then find the eigenvalues. Subtract lambda from this term and from this term. Leave the other two. Set this determinant equal to 0 and solve. 1 minus lambda times 7 minus lambda minus 3 times minus 3 equals 0. Simplify it, so it's 7 minus lambda minus 7 lambda plus lambda squared minus 3 times minus 3 is plus 9 equals 0. Lambda squared minus 8 lambda plus 16 equals 0. Let's solve it up there. So I factored it here and we got lambda equals 4, lambda equals 4. Repeated eigenvalues. So this is the case of repeated eigenvalues. What is the eigenvector corresponding to lambda 1 equals 4, the first eigenvalue? To find the eigenvector, you put the eigenvalue back in there. 1 minus 4, here it is, 1 minus 4, minus 3, 3, 7 minus 4, and then you multiply it by xy, and you set it equal to 0. 1 minus 4 is minus 3, and then 7 minus 4 is 3. So the first equation reads minus 3x minus 3y equals 0. The second equation is 3x plus 3y equals 0. It's the same equation. Let us solve this one. Minus 3x minus 3y equals 0 gives us 3y equals minus 3x. So y equals minus x. And remember, you can pick x or y. I'm going to pick x equals 3, so y equals minus 3. I picked x equals 3, y equals minus 3. Okay, so my first eigenvalue was lambda 1 equals 4. The corresponding eigenvector I picked is 3 minus 3. Could I have picked 1 and minus 1? And the answer is yes. Could I have picked square root of 2 and square root and minus square root of 2? Yes. You can also pick 99 and minus 99. Yes. I picked 3 and I got minus 3. Here's the problem. When you try to find the eigenvector for the second eigenvalue and you put 4 in there, you're going to get the same thing, 3 and minus 3. This is called a defective eigenvalue. Defective. What do we do with defective eigenvalues? I'll give you the result. The proof takes kind of a long time, so I'm going to put it in a separate video. I'll also send it to my class as a document. I'll send the proof as a document. Okay, if the eigenvalue is defective, in order for us to find the second eigenvector corresponding to the same eigenvalue, what we need to do, according to the proof, we need to resolve this equation, but on the right side, we're not going to put 0, 0. We'll put the first eigenvector we got. So we're going to put 3 and minus 3. So I'll put them in red, 3 and minus 3. So our first equation is minus 3x plus 3y minus 3x minus 3y equals 3. Our second equation is 3x plus 3y equals minus 3. Solve either of them. Okay, let us solve the first equation for y. So, or the second one. So 3y, I'm doing the second one this time, equals minus 3 minus 3x. 3y equals minus 3 minus 3x. Divide both sides by 3, so y equals minus 1 minus x. Pick any number you want for x. I'm going to pick x equals 1 this time. X equals 1, so y equals minus 1, which is minus 2. X equals 1, y equals minus 2. So my vector is 1, negative 2. 1, negative 2. And now we were able to get a second eigenvector for this eigenvalue. And again, I'm going to send you the proof as a document, and I'll put it in a separate video. The solution is made of these two independent solutions. First solution is v1 e to the lambda t And the second solution is v1t. Because it's repeated, we have to put a t in front of it. It used to be x, now it's t. Plus v2 e to the lambda t. So, our x1 is just 3 minus 3 e to the 40. And by the way, you can't change these constants now to 1 and minus 1. Our x2 would be 3 minus 3 times t plus 1 minus 2, all of this times e to the 40. So the general solution of this system of equations, I'm going to write it over here, is going to be capital X equals C1 times X1, which is 3 minus 3 e to the power 40 plus C2 times bracket 3 minus 3 t plus 1 minus 2 e to the 40. And that is the general solution. These are the constants C1 and C2. And remember to put a t in front of the original vector v1 in case the eigenvalue is defective. It's not always defective, but for 2 by 2 systems, it is. For 3 by 3 systems and higher, sometimes it is and sometimes it's not. Let's do another example. This one has 3 unknowns, x, y, and z. The coefficients matrix is 9, 4, 0, there's no z term here, minus 6, minus 1, 0, and then the third equation is 6, 4, 3. The eigenvalue, the characteristic equation that helps us find the eigenvalue is going to be 9 minus lambda, 4, 0, minus 6, minus 1, minus lambda, 0, 6, 4, 3, minus lambda. And I'll put lambda in red. So minus lambda, minus lambda, minus lambda. And we need to set this determinant equal to 0. Okay. Let's set this determinant equal to 0. So 9 minus lambda times minus 1 minus lambda times 3 minus lambda plus 0 plus 0 minus 0 minus 0 minus 3 minus lambda times negative 6 times 4 equals 0. Okay. You multiply this way. Okay. Both of these factors have 3 minus lambda in common. Take it out. So that leaves you with 9 minus lambda times minus 1 minus lambda minus times minus 6, which is plus 6 times 4, which is plus 24. 3 minus lambda stays. This will be 9 minus 9 lambda plus lambda squared plus lambda plus 24. 3 minus lambda. This is lambda squared minus 8 lambda plus 15. It can be factored, and you can write it as lambda minus 3 times lambda minus 5. And this is set equal to 0. So the solutions are lambda 2 equals 3 from here, lambda 3 equals 3 from here, and lambda 1 equals 5. I started with 5 because that one is unknown, it's not repeated. So lambda 1 equals 5, lambda 2 equals 3, and lambda 3 equals 3. And we need to find a vector, an eigenvector for each of these. Okay, the eigenvectors are going to have 3 components this time, because this is a 3 by 3 system and 3 unknowns. Let's go back to this determinant. What you can do also to figure out the determinant is reproduce these 2 columns. Rewrite them here. 9 minus lambda, minus 6, 6. Second column, 4 minus 1 minus lambda, 4. We're done with it. And then you multiply this way. You multiply these 3. 4 times 0 is 0, 0 times minus 6 is 0. And then minus the product of these 3, which is 0, product of these 3, which is 0, and then the products of these 3. So it will be like this. A, B, C, D, E, F, G, H, I. Okay, you reproduce the first two columns, A, D, G, B, E, H. So you multiply A, E, I plus B, F, G plus C, D, H. A, E, I plus B, F, G plus C, D, H. Minus G, E, C minus H, F, A minus I, D, B. This is just a reminder, we did this before. It's just a reminder of how I found this determinant. You set it equal to 0 and then you get these eigenvalues. Well, now we need to find the eigenvectors for each of these eigenvalues. So what I'm going to do is this. We'll start with lambda 1 equals 5 and put lambda 1 equals 5 in this equation. I'm going to remove the additional columns we added just to find this and then put 5 in here. We're going to put 5 in this equation. So 9 minus 5, 4, 0. Minus 6, minus 1 minus 5, 0. 6, 4, 3 minus 5. Simplify it, so that gives you 4, 4, 0, minus 6, minus 6, 0, 6, 4, minus 2. The first two lines, we don't need both of them. We can just eliminate one of them because that will give you the same equation. So the first line gives you 4x plus 4y equals 0. Second one gives you the same thing, so we don't need it. Divide both sides by 4, and that gives you x plus y equals 0, which means y equals minus x. That's all we get from the first two lines. And the third line is 6x plus 4y minus 2z equals 0. So that's 6x plus 4y. Y is minus x. So I'm going to put minus x here. Minus 2z equals 0. 6x minus 4x is 2x minus 2z equals 0. So 2x equals 2z, which means z equals plus x. So y equals minus x and z equals x. Let's pick a number for x. I'm going to pick x equals 1. So that means my y is negative 1 and my z is 1. So my first vector is 1 minus 1, 1. 1 minus 1, 1. And that's the eigenvector corresponding to the eigenvalue lambda 1 equals 5. Now we're going to find the eigenvector corresponding to the second eigenvalue lambda 2 equals 3. Again, if somebody had picked different numbers here for x, y, and z, like 2 minus 2, 2, it's fine. They'll get the same eigenvector. For the eigenvector corresponding to lambda 2 equals 3, I'm going to put 3 here. So 9 minus 3, 4, 0. Minus 6. Minus 1 minus 3, 0. 6, 4, 3 minus 3. Okay, let us simplify these. So that'll give us 6, 4, 0. And this is minus 6, minus 4, 0. Same equation, we don't need it. And the third one is 6, 4, 0. And this is good news. This means that this eigenvalue here is not defective. So we don't have to do the extra steps. We can get V2 and V3 from the same eigenvalue. Let's pick any of these lines. 6x plus 4y equals 0. Okay? Divide both sides by 2, so 3x plus 2y equals 0. 2y equals minus 3x. So y equals minus 3x over 2. What I'm going to do is pick x equals 2 this time. If you pick x equals 2, then y equals negative 3 times 2 over 2. Y equals negative 3. So I picked x equals 2, y equals negative 3. Now for z, I can pick anything because the third column is 0, so 0 times any number is still 0. So I can pick z equals 99, or I can pick z equals 1. So z equals 1. X equals 2, y equals minus 3, z equals 1. 2 minus 3 and 1. And that gives me the second eigenvector. For the third eigenvector, I'm not even going to bother with x and y. I'll pick a number for z. For example, I can pick z equals 1. And 1 times 0 is still 0. But this time I'm going to pick, to make this equation work, I'm going to pick both x and y to be 0. Z equals 1, x equals 0, y equals 0. So let's see. 6 times 0 plus 4 times 0 is still 0. Plus 0 times z, which is 1, is still 0. So I'm picking 0, 0, 1 for this vector. 0, 0, 1. Let's see. 6 times x, which is 0, 0, 1. 6 times 0 plus 4 times 0 plus 0 times 1 is equal to 0. So that's the third eigenvector. So we were able to get 3 eigenvectors, 1 for lambda equals 5, and then 2 different eigenvectors for lambda equals 3. Now that you have the 3 eigenvalues and 3 eigenvectors, the solution is C1 V1 e to the lambda 1t, which is C1 first vector times e to the 5t, plus C2 second vector e to the 3t, plus C3 third vector e to the 3t. And you can leave the solution like this. Or, if you wish to separate x, y, and z, then small x is C1 e to the 5t plus 2C2 e to the 3t. Here it is. Small y is minus C1 e to the 5t minus 3C2 e to the 3t plus 0. And then small z is C1 e to the 5t plus C2 e to the 3t plus C3 e to the 3t. You can write the solution like this or like this. And this completes the repeated eigenvalues lecture.